let us continue our discussion of fluid flow. So we have already discussed orifices, those that discharges at the bottom. So the jet produces a falling head. Then orifices that discharges at the side of a wall or a tank. Orifices that discharges on the inclined side of a tank and therefore produces projectiles. Then let us continue our flow measurements using flow meters such as the Venturi meter, the pitot tube, and the nozzles. One of the instruments or devices used for measuring flow is the Venturi meter. The Venturi meter is a flow meter that was invented by Clemens Herschel, and which was named in honor of an Italian mathematician, Giovanni Venturi. So this is how the Venturi meter was used by Venturi and by Herschel in determining the fluid flow. So describing the Venturi meter, it is a flow meter that is attached to a pipeline. Okay, so we call this is the entire Venturi meter in the figure. So this is the inlet. We call this point 1 as the inlet, where the discharge passes through at point 1, which is the inlet. The inlet is the same size as the pipe, and then the discharge goes through a constricted opening which we call the throat. So take note of the convergence of the diameter from point 1 to point 2. So itong entire assembly na to from 1 to 2, yan yung tinatawag na Venturi meter. The velocity or the discharge is constricted from the inlet towards the throat. Now, if we take, again, I already told you so many times that the Bernoulli's energy equation is applicable to flow meters. We write Bernoulli's equation between the inlet and the throat. So this is the velocity head, pressure head, and elevation head at point 1 is equal to the total energy at point 2. So ito yung Bernoulli's energy equation. If we are going to rearrange these quantities, we have b sub 2 squared over 2g minus b1 squared over 2g, transpositioning the quantities. So there is an increase b sub 2. The velocity at this point 2 is much faster than the velocity at point 1. So there is a change in velocity from b1 to b2. Okay, and then rearranging the pressure quantities and the elevation quantities, ito yung ating Bernoulli equation. So, the equation is stated in the Venturi principle that for every increase in kinetic energy, there is a corresponding decrease in the potential energy. That is the Venturi principle. Now, if we want to solve this equation in terms of the discharge, for example, we apply the continuity equation. Kung ano yung volume na pumasok dito sa pipe 1 through the inlet is the same quantity that passes through point 2. So, yun yung equation natin of continuity. And then, if we want to solve for B1 in terms of B2, this is your equation. So, reiterating the Venturi principle, for every increase in kinetic energy, there is a corresponding decrease in potential energy. This is the equation form of the Venturi principle. Increase in kinetic energy, there is a decrease in potential energy. If the Venturi meter is horizontal, that part, Z1 minus Z2 of the equation is cancelled. Okay, so let's have our first problem on Venturi. Okay, let us read the problem. In a test to determine the discharge coefficient of a 5 cm by 1.25 cm Venturi meter, the total weight of water passing through the meter is 3,420 newtons in 5 minutes. the differential gauge show the mercury water to have a deflection of 38 centimeters. So we are required to find the coefficient of discharge, C. Okay, so let us solve the problem. From what is stated in the problem, the discharge passes through the inlet and the throat, and the pressure difference between the inlet and the throat can be obtained using a manometer with mercury as the gauge fluid. As shown in the figure, it discharges a weight of 3,400 newtons in 60 seconds. Okay, 60 seconds. Okay. So, applying the Venturi equation, Z1 and Z2 is cancelled kasi naka-horizontal naman yung ating Venturi meter. And then we solve for B1. In terms of B2, we have B sub 1 in terms of B2 is 0.0625 B2. Substitute natin do sa unang equation natin. We have 0.996 B sub 2 squared over 2G equal to P1 minus P2 over the unit weight of the fluid, which is water. Now, how do we solve this part of the equation? Manometer problem tayo. So, from the manometer reading, pressure at 1 plus the unit weight of a column of fluid that stands X and 0.38 centimeters, ayun, is equal to the pressure at point 2 plus the unit weight of water that stands X meter plus the unit weight of mercury that stands 38 centimeters. So, ayun. So, we simplify the equation that we obtained, expressing this in meters of water, the difference in pressure between 1 and 2, the inlet and the throat, in meters of water is 4.79 meters. So, isa-substitute natin dito, we solve for B2. Okay, B2 is 94.36 meters per second, and that is obtained using the head, so it is a theoretical velocity. So, using the theoretical velocity, we find the theoretical discharge area times velocity is 1.23 liters per second. Now, the actual discharge can be computed by finding the volume discharge per unit of time. So, yun yung actual. 0.00116 cubic meter per second. The ratio between the actual and the theoretical, we solve for the coefficient of discharge C, 0.94. Okay, so let's have another problem. This time, the Venturi meter is assembled in a pipeline that is discharging upward. So, vertical siya. So, you see here the quantities. The inlet and the throat is 300 millimeters distant from each other. Then we have a manometer attached to the inlet and the throat, showing that a gauge fluid with specific gravity of 1.5 shows a deflection of 800 millimeters. So, pag ginamit natin ang manometer equation, dito sa manometer equation na yan, which is, sorry class, this is a little bit abbreviated solution. So, again, we use the Bernoulli's, Venturi's principle. Okay, ito yung ating Venturi equation. So, ang kailangan natin dito is the difference in pressure between the inlet and the throat. So, kuhanin natin yung manometer reading. Ito yung kanyang, ito na yung kanyang abbreviated solution. Pero ito, kaya nyo na itong kuhanin. So, the pressure at 1, okay, the pressure at 1 is equal to P1 plus the unit weight of water that stands Y. Okay? Then the pressure at 2 is equal to the unit weight of the fluid that stands X plus the unit weight of the fluid that stands 800 millimeters. So ito, makukuha nyo na yan. May shortcut na yung aking pagkuha nun. Then also from the same figure, we note that this height is 300 mm plus y equal dun sa height na yon, that is x plus 800 mm. So we solve, if this equation yields a value in terms of x minus y, from the figure x minus y is negative 0.5. So we just substitute and you solve for the pressure head difference between the inlet and the throat in meters of water equivalent to 0.8. So pag sinubstitute natin dito yan, okay, so this is 0.7 plus the difference in the elevation between 0.1 and 0.2, which is negative 0.3. So the velocity head difference between the throat and the inlet is 0.4. So pag nakuha natin yung 0.4, okay, we go back to the comparative equation between velocity at 1 and 2. So V1 is equal to B sub 2, diameter 2 over diameter 1 squared times B2. So yung diameter ng inlet is 150, no, it's 300 mm, and this is 150 mm, ayun. Substitute and solve for B1 in terms of B2, and then you substitute. So we solve for B1 is 0.723, B2 is 2.89. As it is, these velocities are theoretical velocities which can be used to solve for the actual, because C is given as 0.97. So the actual discharge is 0.049. Okay, another flow meter is the nozzle. Okay, describe natin. A nozzle is a converging tube connected at the end of a pipe or a hose used to create jets and streams, and also used for metering. So yung nozzle parang similar to the Venturi meter. The only difference is that the throat is issuing in the atmosphere, and therefore wala tayong the pressure at point 2 is atmospheric, so it is 0. So if we write the Bernoulli's equation, ito siya, itong pressure at 2, which is the discharging end of the nozzle, is 0. So it is similar to the Venturi. There is convergence from the inlet or from the source, which is the section of a pipe or a hose, is converging towards the discharging end at pipe 2. So there is the stream issued from this point 2 is called a jet because of the faster velocity. So ito lang yung equation natin. Okay, we can also say that if the hose or the nozzle is horizontal, Z1 is equal to Z2. So ito na lang yung ating equation. Then to compute for the head loss, again, you always memorize this formula for finding the head loss through the nozzle, similar to finding the head loss through the orifice and through the Venturi meter. Okay. Thank you for watching. I hope these problems help you understand more our lessons on fluid flow.